engineer who's working on NASA's Roman telescope, Roman Space Telescope. He's got an engineering physics degree from Cornell, an optics degree from U of R, and he was the chief system engineer on the James Webb Space Telescope, originally starting in 2002 under Kodak at the time. They later became L3 Harris. So there he is, Dr. Tony Whitman. Okay, so we didn't touch base before I started. Would you like to put your slideshow on this computer? Or do you want to hook up yours?
Probably easiest.
Okay. So let's
Dr. Tony. Thank God.
Almost there. For whatever reason, I can't move the. Oh, there it goes. No, it's working now. All right, thank you. So I guess the skies may not cooperate tonight, so I'm your entertainment. So I'll do the best I can. I have a bunch of stories on Rochester's contribution to the James Webb Space Telescope. Some of this, if you went to my planetarium talk, some of this is a repeat, but I also have new stuff in here. First of all, are you well versed in meters and Kelvin, or should I stick with feet and Fahrenheit?
Both will work.
Both will work. Okay.
I like Fahrenheit.
All right. So I'll try and flip through this quickly because I think maybe a lot of you know this, but if not, just stop me or slow me down and ask questions. So when the Webb telescope idea started, there were basically four main themes that they wanted to design a telescope for. A lot of this, you've seen the pictures already, but of course back then it didn't exist. So number one, wanted to see light all the way back to the beginning of the universe that we know today. And also the assembly of galaxies, stars, planets. So in order to see light back to the beginning of the universe, it needed to be, depending on where in the spectrum, 10 to 100 times brighter or more sensitive than the Hubble telescope. It also included spectrometers and a chronograph. And we also had to see through dust clouds in order to see the birth of stars and planets. So a lot of publicity on TV, et cetera, but just to give you an idea of scale, this was a full mechanical scale that was set up in the parking lot at the Rochester Science Museum.
When was that?
It was in the 2000s, like late 2000s. So it's an old picture. It was later than that. No, either the internet is unstable or the speaker is unstable. So, and as you know, so the left is the picture from Hubble, right is a somewhat similar picture with Webb. And you can see how many more stars you can see within all that dust. Now, another reason for going infrared is the Doppler effect. I assume you're familiar with the Doppler effect. I can explain it if you're not, but we wanted to be able to pick up from stars and planets. We wanted to be able to see methane and carbon dioxide, water, et cetera. Since we learned from Hubble that the farther out you look in space, the faster that object was moving away from us. The faster that object is moving away from us stretches the wavelength into the red, near infrared. If you want to look at galaxies way back at the beginning of time in our universe, you're talking 13.5 billion light years away. By then, the objects are moving so fast that a visible spectrum is shifted all the way into the mid-infrared. So just schematically, you can see to the right, at the bottom is a star close up, further away is the galaxy. You see the spectrum shifting to the right, and then a galaxy much further away, and then a galaxy, back at the beginning of time is shifted further to the right. So if you want to see visible light at the beginning of our universe, you actually have to look in the mid-infrared and shift it back to convert it to visible light. So that's two reasons why the Webb was designed for infrared. The Hubble was not designed for infrared. So I won't be able to help much with many astronomy questions. I was more on the engineering side. So when you think about infrared, as you know, heat gives off radiation infrared. So this man's arm inside a black plastic bag, the infrared generated by the heat from his arm passes right through that plastic bag. So with the infrared camera, you can see his arm through that black plastic bag. So it's the same reason why you can see infrared light coming from a star inside dust. So operating in the infrared means that the heat from your telescope also generates infrared. And so if we operated at room temperature, like this man's arm, we would flood the detectors and we wouldn't be able to see any stars. So that means that we have to have the telescope cold. And by cold, it's the mirrors are around 50 Kelvin or negative 400-ish degrees Fahrenheit. So that means we had to design and build a telescope at cryogenic temperatures, which added to the challenge. So this is a blown up view of the telescope. You're familiar with the segmented mirror, all the actuators behind it to move those segments. The secondary mirror is about 26 feet out from the primary mirror. The instruments or detectors are about the size of a minivan. So that inserts inside that covering that's shown there, and that whole thing inserts inside the back of the backplane there. So our responsibility was the building and testing of the Webb telescope, but we also had some flight hardware. For example, we supplied the struts that hold the instruments module to the backside of the primary mirror, and we also mounted one of the detectors to the camera, to the one of the detectors in the lower right. So the other interesting aspect of the Webb telescope was that it was not only NASA covering the build, design and build of this telescope, but Europe and Canada was also involved. And where their involvement came in, Europe supplied the rocket that blasted this into space. Canada supplied the fine guidance sensor, which is in the back of this. Fine guidance sensor, so you're familiar in your telescopes, you want to lock onto your object. And in this case, you're not so much following it, but in this case, you want to compensate for any dynamic movement of your telescope. So you have to lock on really tightly because we're taking long images, we're counting photons. So we want to lock that as tight as possible to collect those nice clear images that you saw. So the analogy that they used was that if you were playing laser tag with your friend in Los Angeles, if your pointing control of that laser was as good as the Webb, you would be able to keep that laser on your friend's forehead out in Los Angeles. That's how tight the control is in the Webb telescope. And I talked about 10 to 100 times more sensitive than Hubble. The analogy they use there is if the Webb was here and could look at the moon, it could detect the heat signature of a bumblebee's wings on the surface of the moon. So that's how sensitive the Webb is. And yet still, when you're looking at those galaxies that are 13.5 billion light years away, you're literally counting photons of light to create those images. So the Canadians provided the fine guidance sensor. The Europeans provided the near infrared spectrograph and the mid infrared instrument. The US, which was primarily University of Arizona and Lockheed Martin, supplied the near infrared camera. And just to give you an idea of the size of the detectors in these instruments, you can see the hands next to a pair of detectors there. So at the beginning of this project, a lot of things didn't exist at the beginning of this project, and one of the things that didn't exist was infrared semiconductor detector material of the size that we needed for this telescope. One of the groups that helped develop it was the University of Rochester. So that's another Rochester connection. So our role, as I said, was building and testing the telescope. And it took 2 years just to figure out how the heck we were going to build this thing. At the time, it wasn't really even fully designed yet. So we had to figure out how to build it without exactly knowing what it was going to look like. But in the end, you had to have, so you see these large box beams that was used in the construction here. One of the things we figured out was that the precision that we needed for integrating those mirrors onto the structure was within less than the width of a human hair across that 26 feet. So we needed a good stable platform to not only hold the telescope, but keep it stable so that we can use what we used was laser trackers, laser beams, laser technology to measure distances. So it was hard enough getting less than the width of a human hair across 26 feet. Any of you who have mismeasured the location and where to put a window on a house can understand what that's like. But also, since we're limited by how much mass this rocket could launch out to the L2 orbit, the structure was very lightweight, and it was so lightweight that in 1G, in Earth's gravity, there was a lot of sag to the structure. And every time you put a mirror on, that shape changes. So not only do we have to be very precise in our placement, but we also had to calculate, we had to put everything perfectly in 0G while we're here on Earth with everything sagging. So every time you put a mirror on, you had to calculate using finite element modeling, calculate that complicated structure and understand the change in the shape after you added that mirror segment, so you knew exactly where to put the next mirror segment, which will also affected it, and so on and so forth. So this is a picture of there's a lot of stuff on YouTube, but I found that typically the connection to the internet to YouTube takes too long for a quick talk like this. So you can go on YouTube and see videos of all of these things. So this is a picture of the instrument module going into the backside of that. See if the internet connection comes stable again. Going into the backside of that backplane, the primary mirror is down below. You can't see much of it, but you can see the structure sticking out. This is after the primary mirror that's been completely integrated. It's flipped over, and now we're putting the instrument module on. There's only like an inch to spare between the instrument module and the frame on that backside. All of this is made with carbon composite material. And so if you scrape it at all, you run the risk of breaking a fiber and then This whole thing is very carefully designed to its limits in order to keep the mass down, keep the strength up to last launch. So you break a fiber, then it's like, oh no, are we in trouble? Do we still have enough strength for launch, et cetera? So that's why it's an extremely careful process, lowering that in there and then finding the right alignment and attaching it. So all the calculations that go into this, so let me give you a feel for that. So as I said, the instruments were made by the Europeans and University of Arizona. So we had to take their information on all of their alignment data and their 1G to 0G conversion. The structure here and the buildup of those instruments, that was done by NASA. So we had to take their information on their alignment and their 0 to 1G information. The mirrors down below, those assemblies were done by Ball Aerospace. So we had to take the information from Ball Aerospace, and the backplane was made by Northrop Grumman. So we had to take information from them. So you can imagine the communication, all the different communication that had to occur to get all those numbers, get it in the exact format that you want it in, and make sure there's not a mistake anywhere in there. A lot of you probably have heard of the rover that crashed into Mars because someone made a mistake converting inches to millimeters. Very careful calculation through that whole process. And a lot of nervousness because you've got $1 billion instrument module going into the backside of the $1 billion telescope. So lots of flies on the wall watching carefully to make sure you don't make a mistake. So this gives you an idea of all the companies that were involved in this project all over the United States, Europe, and Canada, as I said. This is a close-up of the Rochester area. I think they went down to a certain money threshold because I know we worked with twice as many Rochester area companies as what's listed on here. But an interesting story here for any of you familiar with Phelps. I got a call during this project. So the mid-infrared instrument operates at 6 or 7 Kelvin. That's 6 degrees Celsius above absolute zero, where electrons stop moving. Very cold environment, and they needed a valve that operates at that temperature. And they searched all over the world for a valve that could operate at that temperature. And the only place came from a place in Phelps, New York. They called me and said, "Have you ever heard of Phelps, New York?" And I said, "Yeah, they have a sauerkraut bowl there." So as I said, so this telescope is very big, and we want to operate it very cold. And one of the few chambers that existed that was big enough to test this at temperature was the chamber that was used to test the lunar module back in the 60s. Now, interesting enough, engineering today is very carefully done on a computer with computer models. Back then, NASA projects were very different. They built this whole chamber in a year, and they just operated it. And actually, so the whole thing went up in a year from the first dirt shovel to a built chamber, and then they built the building around the chamber. So within a year it was up and operating. They pulled vacuum on it, and the door bent in. So they said, "Oh, okay, we got to make that thicker." So they replaced the door with a thicker door, and then off they were running. There's no way that NASA would allow that to happen today. So this chamber is 120 feet high and 65 feet in diameter. So roughly 12 stories tall. And so we had to cool that whole thing down to 18 Kelvin for a background, which is below the point where oxygen freezes and nitrogen freezes. So one of our, and obviously you don't wait until you have the flight telescope before you try it out. So one of our tryout tests with some of our equipment in there, there was a leak, and it was I want to say it was like a 30-day test because it takes a while to cool down. And we calculated, so 120 feet tall and 65 feet in diameter. We calculated the leak was about a 1/4 inch. So those guys had to search that whole chamber to find that 1/4 inch leak. So we calculated that. Well, okay, we can make it to the end of the test. We had nothing important in there that would get damaged by things freezing onto it. So so it was really cool because quickly this is through one of the portals in the chamber, you could see frozen nitrogen on the left is very grayish color, and frozen oxygen on the right is a very bluish color. So that was pretty cool. I've never seen that before. And of course, as you know, oxygen is very flammable, so you can imagine what frozen oxygen is like. So when we went to test this telescope, we needed 7 18-wheeler trucks a day of liquid nitrogen to cool it down. The actual flight telescope on the left, you can see how tightly it fit into that door. So as I said, this was built in the 60s. The blueprints that we found actually didn't match the chamber because there have been so many modifications over the years. So we actually had to get surveyors in to find out exactly where that door was relative to, we used rails on the floor to roll the telescope in, and then we lifted it up while it was in the chamber. So we had to precisely calculate where it was and how much clearance we had. We ended up with, we figured about 8 inches margin at the top. But the night that this was going into the chamber, I got this frantic. So I was actually home that night resting up because I was in charge of the testing. So I was home resting up because I was going to go down for this 100-day test. So I got this frantic call at 10 o'clock at night. It's not going to fit. How do you know it's going to fit? Calm down, calm down. We knew about this about 3 years ago. We figured it out. And we had a plan B if it didn't quite fit at the top, but we didn't plan B. It went through. So almost all the test equipment that you see inside this chamber was built in the Rochester area and trucked down to Houston, Texas, where this chamber is located on Johnson Space Center. In the left, behind the flight telescope, that was all thermal simulated, thermal simulated, although we were also handling the electrical cables that connect to the telescope. That was to simulate the spacecraft, the heat coming off the spacecraft and the heat that was leaking through the sun shield. So that's what that was all about. In the middle, so this whole telescope suspended from isolators at the top of the chamber to isolate our measurement from the general environment. Things like trucks driving on the road nearby. So you can imagine a bunch of us Yankees came down right to Texas, and we told them, look, our measurement is extremely sensitive. We don't want anybody walking around the chamber while we take our measurement. Well, they thought we were full of it, right? Who are us to tell them what they can and can't do around their chamber, right? So one of our measurements, we got this anomaly. We're like scratching our heads, trying to figure out where it was coming from, trying to match frequency from our test equipment and the equipment operating in the chamber, and having difficulty matching the frequency. And but we knew exactly what time of day it occurred, and the people who operate the chamber, which are from the Johnson Space Center, have careful logs on when things occur. And sure enough, our time matched up to somebody walking around the chamber. They're like, "You detected that?" And I said, "Yes, I told you we were detected, so don't walk around it." So gave us a little more respect after that. So the whole thing hangs from the isolators up at the top. That's to keep it vibration free. There's a center of curvature. You kind of see the, maybe if I use this box here is full of center of curvature optical measurement instrumentation to measure the quality of that primary mirror and also to phase it for the first time. And that was made all over Rochester. We actually had to invent a certain null lens for it, for the shape of the mirror and the multi-segment, because this is the first time ever that we did a multi-segment primary mirror. And that null lens was built by a company in Sodus, New York. We also used a wave meter from Fishers, New York, because we needed to know precisely the wavelength of the laser. Otherwise, we would measure the wrong values. So that was a center of curvature optical assembly, otherwise known as the COCO, which I'll show in a minute. Below that are 3 flat mirrors to measure light that we injected into the telescope. More about that later. That whole apparatus at the top was about 9 tons. So we were hanging 9 tons over this multi-billion-dollar telescope at 18 Kelvin. Had to make sure it worked. You also see 4 windmills around the perimeter. Those are photogrammetry cameras. I'll talk more about that later. And a bunch of white dots. So the beginning of this project, there were all kinds of questions. We had experts from all over the country thinking that there was no way that we were going to be able to test this to how well it needed to be tested, including professors from University of Rochester, University of Arizona, MIT, etc. But we worked through it and had it work at the end. So this is a close-up of that center of curvature optical assembly, or COCO, as we called it. So it was in the 100 Kelvin regime. So we had a liquid nitrogen shroud through the whole chamber, and then inside that was a high pressure gas helium shroud to get to the colder temperatures. Nitrogen only gets you to 100 Kelvin, which is something like negative 350 degrees Fahrenheit. But we need to get down to negative 400, close to negative 450. So in order to get to that extra temperature, we had to have a colder gas, which was helium. So, but as you know, with precision optics, it's a lot easier to make that at room temperature. So the inside of the COCO is actually at room temperature, and as you know, light going through a window gets degraded. So we did this without a window. So the whole thing, in order to keep it at room temperature, the whole thing needed to be wrapped in space blankets, which is what you see in the right. This was about 52 feet from the primary mirror. That was the center of curvature length. So anyway, an idea of the complexity. The other thing we had to figure out, and there was some invention involved. So as you know, light is cyclical, has phases. So you can have 2 segmented mirrors that look like they're in phase and perfectly aligned, but it turned out they're exactly 1 phase apart, or 2 light cycles apart. So how do you know if you have this condition versus this condition? So we figured out we could beat 2 wavelengths together and essentially form an effective wavelength. And we were able to design this to measure the the equivalent of over a millimeter wavelength. And then step our way down to Heaney wavelength. So talked about photogrammetry. Photogrammetry uses parallax. You're very familiar, probably very familiar with parallax. You know, if I take a picture here of you relative to this laptop, you're going to be a certain relative position in the picture over here. If I now take a picture over here with my laptop in it and you, obviously in a different position. And so the idea here, we had 4 cameras and windmills taking pictures all over the place, all different angles. And if you use enough pictures and enough math, you can measure the relative alignment of parts in this telescope, again, to within the width of a human hair. So same technique is used with crash dummies in cars, etc. They put all the white dots and they take lots of cameras. So that's why you see white dots mounted to the telescope. And this isn't purposely over to saturated picture from one of the cameras. So you can see all the white dots that show up. So we took advantage of the Cassegrain focus that occurs in the just above the optics of the telescope to put optical fibers in there to inject light down through the telescope and also inject light up to the secondary mirror down to which bounced back down to the primary mirror, which bounced to those flat mirrors at the top. And then the light retro reflected from those flat mirrors at the top and went through the whole telescope. And so that's how you could test the whole telescope and not just the primary mirror. So we had 100 days to cram as many tests as we possibly could. A lot of this stuff was done for the first time. So as soon as we had multiple groups involved, we had the instrument teams, we had the telescope team, we actually had a day or two where we're commanding from Baltimore, Maryland down to Johnson Space Center, simulating as if this was in orbit and running through commands and telemetry that way. There's the IT people, thermal engineers, the optical engineers, the contamination control engineers. They all had their own agenda. The software, the flight software team, they all had their own agenda. They all needed particular orders for specific tests. So this is just a snapshot of, this was just a high level view of what was happening each day. And one of my jobs and one of my helpers was constantly re-optimizing that, because somebody would have a problem. We would tell them to go work their problem, and then we rearrange and re-optimize other tasks to fill in the time. So right in the middle of that, the most dangerous time for the telescope was when it was at its coldest temperature. The telescope takes about a month to cool down. And so you can't just stop the test and let it warm up on its own, because it will break itself. The temperature would change too quickly. You have to have a controlled warm up. So right in the middle of that, Hurricane Harvey showed up. So you can see us driving in for our shifts. So the hurricane had these spiral arms. So we actually had a meteorologist tell us when the gap in the spiral arm would occur. And then text would be sent out for the next shift. So we would do a shift change between spirals, and then the next shift would run during the spiral. So just an idea of the fun that was involved. And since then, of course, you've seen all these great images. So I told you about that hard gravity problem. The instrument module and the telescope, we actually flipped it the other way and tested it at Johnson. So we knew we got that part right, but we didn't know whether all the mirrors were in the right spot until we got that first image from space. So when I saw that, I was very relieved. All right, we did that calculation correctly. So that's Webb. And this is what we're working on today. It's called the Nancy Grace Roman Space Telescope. It has a resolution as good as the Hubble, but takes pictures 1,000 times faster. In fact, it'll take data so fast that there aren't enough people on the Earth who can process that data. So they're just going to take that data and make it public from day one, because they know you can half at it and do whatever you want. There's plenty left over for someone else to take the data and do something else. So what's the reason for this? Obviously, we get a wide field survey of the universe in infrared. It's to help answer the question of what happens to the universe after this. Is it expand at a faster and faster rate? We call it the big rip. Or does it expand and slow down and start coming back together? They call that the big crunch. Or does it just keep going the way it is for a while? The astronomers, so we also have a far fancier coronagraph on it than what's on the Webb. The Webb essentially just has a simple knife edge for a coronagraph. So you just move the knife edge over the star and take your light from the planet nearby. The Roman has an extremely fancy coronagraph. I'll show a graph in a little bit. So it can. The astronomers tell me it will find more exoplanets than all the exoplanets found so far. So as you know, when you look through your telescopes, you're looking at less than 5% of the matter and energy in the universe. So one of the purposes of this is to try to understand dark matter and dark energy better. And to give you an idea of the coronagraph, you can't read it to the left here, but this is flux ratio to host star, basically the brightness of the planet relative to the brightness of the star. This is the separation between the planet and the star. And this is where we are today with JWST and Hubble on this curve. This is where Jupiter is. So we predict that Roman will be able to see the equivalent of a Jupiter next to a star that's the equivalent of our sun, and actually take an image of that planet. And of course, the Holy Grail, but we have to prove this out, and we're learning a lot from the Roman telescope. The Holy Grail is to get down to the Earth. Won't get there with Roman, but we're learning a lot. So the next one, we can get there from here. It's all about temperature stability. So just to give you an idea of why it's 1,000 times faster, this is the field of view of the Roman Space Telescope relative to the field of view of Hubble. And also we're going to an L2 orbit, whereas Hubble has to rotate around the Earth. So the Earth gets in the way all the time. And, so that's two of many reasons why it's 1,000 times faster. So just give you an idea of the field of view. And this is the construction. What we're building here in Rochester. Can't see the cursor too well, but we're building see what's built as the imaging optics assembly. That's the part we're building in Rochester, and that will ship to NASA, where they'll put two instruments on it, a wide field instrument and a coronagraph instrument, and then the barrel around it and the solar panel and so forth. This is almost what the Roman looks like today. So we already have the secondary mirror built up over the primary mirror. This was taken a few months ago. Since then, what's labeled as the POMA, that's the pickoff mirror for the coronagraph, that's already installed. Next to that is the TOMA, that's the aft optics for the coronagraph. That's already been installed once, and the shim's calculated and alignment checked, and then we removed. We're now in the process of integrating the aft optics for the wide field side. What's labeled as the We're also working on a laser interferometer space antenna for gravity waves. This is for the European Space Agency. We've already built a engineering model to test how stable it is for this measurement. And now we're in the middle of process of building an optical engineering model to prove out the rest of the concept. European Space Agencies, has plans to start building the flight model in about a year. You've heard about the gravity antennas here on Earth. I think LIDO is one of them. But on Earth, you're limited to something on the order of a kilometer wavelength. Whereas in space, this is called LISA. LISA, the sensors will be about 1 million miles apart, so you can detect much longer wavelengths. And last, we're always talking to NASA about what we're doing next. What they want to do is be able to capture images of 20 to 40 Earth-like planets. So we're figuring out how the heck we're going to design and build a telescope to be able to do that. So that's in the concept phase right now. And it's all about extremely tight thermal stability. You're familiar with sub-wavelength performance, and on Webb we would talk about nanometers like noise that we had to make sure we're under a few nanometers in order for it to work. This one we're talking tens of picometers or 100th of a nanometer stability. So definitely a challenge for the next group. That's it. I have more stories, but I don't know. I don't want to take too long, so
Question.
sure.
I know the technology in James Webb was kind of frozen in 2006 or 2007, right?
Roughly, yes.
And what about the technology in the Roman telescope one, or has it reached that point?
It's frozen at this point. Most of the technologies on the coronagraph side. This is really the coronagraph is more a technology demonstration for NASA, kind of to prove that the design works. So a lot of new things in that, a lot of new thermal control of the telescope that we developed to make that tightly controlled so that we can do pornography for Jupiter-like planet. Everyone's building now, so the technology is done. All the parts are in, and we're putting them together. Couple of advantages with this, with the Roman telescope. We're using the detectors that were developed for Webb, so we didn't have to invent new detectors. The mirror is 2.4 meters diameter, just like the Hubble, but it's about a quarter of the weight. So that we've taken advantage of technology development since Hubble for that. So that being a quarter of the weight enabled us to add a chronograph instrument to it and still meet the mass of the rocket. But it's Hubble-like technology in the telescope, which except for the temperature control part, so and the lightweightedness. So that made that part easier, and that's why we're building it much more quickly than the Webb took. We're already in the building stage and won't be done. So
What's the target launch date?
mid 2027.
Can you explain a little bit more about like what it takes to keep something that thermally stable and stays that cold the temperature? How do you maintain that for such a long time?
Salt meters and lots of temperature sensors. Really what affects us temperature wise. So if we were just pointing at a single spot in space, space is vacuum, it's got a uniform thermal environment around it. That would be very easy to control, but obviously we're pointing to different directions in the sky. And so the bugaboo is the sun, changes its angle relative to your telescope, which changes the temperature gradient and so forth. So that's fighting against its changes due to where you're pointing relative to the sun.
Any more
I have a
questions?
question online.
Sure.
Okay, and I just posted it, but I'll state it. What were your first concerns when you were at Johnson and Harvey came through?
So we were fortunate in that there was a tropical storm about 2 years previous when we were running one of our practice tests. Tropical storm David, which was like Harvey, but it was only night, whereas Harvey was like 3 or 4 days of constant rain. We had 52 inches in 3 days. So those of us who were there during that tropical storm, which wasn't the whole team down there, so there's still some, panicking going on, but obviously the people from Houston are used to it, and those of us who made it through that previous tropical storm kind of knew what was coming. So concern, of course, was keeping a little bit keeping the telescope safe, but actually a large vacuum chamber, airtight vacuum chamber is like the safest place it could be. So it's just making sure you kept power and your electronics going, making sure that didn't get wet. We actually had 2 substations feeding us with power. So that helium refrigerator took something like on the order of 100 megawatts if we changed temperature really quickly. So a lot of power. But we had redundant substations feeding us, but there's still a chance that both those substations go out. So we also had a diesel generator connected. And diesel generator was designed to keep things running enough to be safe, but it was but still there was water coming. So this building was built in the 1960s. The roof was good. They had put a new roof on, but the rain was coming sideways as well as vertical. So there was actually rain coming in through the walls. So that first night we were running around, basically plugging holes in the dike. And we actually, I didn't put that picture in this PowerPoint, but we actually built quick little frames of plastic over our computer monitors and electronics to keep the water out of it. So it was interesting.
Thank you very much.
Oh, and another worry, pseudo worry. First experience I ever had where there was difficulty getting food. In fact, the hotel where I stayed at, by the third day, the free breakfast that you got was the leftover salad bags. That was it for breakfast. But before this came, a lot of the grocery stores shut down right away, but some of the mom and pop places were still open. So we drove around and raided the mom and pop places. The only thing that was left was like expensive, like there was tuna that was like $10 a can that had, fancy spices in it or something and stuff like that. So we stocked up on food, but we even went through that. Now we weren't really in danger because we had these MRDs from the Army there, but everybody said, if at all possible, avoid the MRDs. So we did manage to avoid the MRDs, but it was challenging. Anyway. Got a question in the room?
What level of vacuums were you reaching the chain?
We were down to, the advantage is we had that huge cryogenic shroud, which sucked, below the freezing point of oxygen. So it sucked everything out of that air. So we were down below 10 to the -8 torr.
10 to the -8.
Yes. Yeah. Yeah. Any more questions on the phone?
I'm waiting to see if somebody.
Just typing.
So how cold is space and how much of a vacuum?
It's a perfect vacuum, even lower than 10 to the -8. The background temperature of space is 3 Kelvin. It's actually the leftover radiation from the Big Bang. So, our calculations are based on that 3 Kelvin temperature as the background in most directions except the sun, the earth, and the moon. The Webb telescope was designed to be passively cooled, so it was relying on that 3 Kelvin to remove all the heat from the electronics running the telescope.
One other question from Zoom. So how did I know actually, and you probably know Joe Howard, who is the optical design guy for
Yes.
James Webb's.
Yes.
And
Normal.
so how did you feel, when James Webb launched? You've been working, and in the case of Joe, he'd been working on this for 20 years. What was that
Yes.
experience like to kind of watch it, launch off the launch pad and actually get to where it was supposed to go with all those single points of failure that the news media
Yes.
likes to talk about? What was that like for you?
Right. It was very nerve-wracking. And it lasted 2 weeks because I really couldn't feel relief until the secondary mirror was deployed. That was like the last part that had to work. There were other things that had to work, but all those other things we tested at Johnson Space Center. So I had pretty good confidence. Once that secondary mirror was in position, the deployment of those segments, I had confidence that would work, and we would get that phased. So it was 2 years of nerve-wracking. Now, most of those deployments, Northrop Grumman had designed and built, so they were very confident based on experience they've had doing that sort of thing in space. But still, even see, I have to be careful with what I say, but even if you have something like 99.99% chance of success, take that to the power of 300 and whatever it was, 350 single point failures, and the probability isn't that high when you do a simple math like that. Fortunately, most of the public doesn't realize that. So if they knew the probability of it working when we launched it, they would have been upset that we spent that much money on it.
Did you celebrate? And if you did, how'd you celebrate?
It's hard to have a 2-week long celebration. There's a little bit of celebration as we made each milestone. It was probably more a feeling of relief when that first star showed up, that really sharp star. Then a lot of pride because wow, it's better than it can be diffraction wise. So everything worked. It's actually working. You always calculate the worst when you design this, and you calculate a worst case, you calculate a probable case, and it's operating better than even a probable case. So we're extremely happy with it. So at work, we had a watching party with a cake, and it was my first experience. I felt like I was running for office or the paparazzi because I had cameras and microphones all around me for an interview for the local evening news from all the channels. So that was my celebration. I was talking to them.
Awesome, thank you.
But when I worked for a satellite back in '89, and I met people who had worked on the design and development and build of that satellite for 30 years. And I had just graduated from U of R. I was like, oh my word, I would never, back then it was a 5% chance that your satellite would end up in the ocean. Rockets, the best rockets were 95% successful back then. So I was like, oh my word, 30 years of your career on this one thing and it could end up in the ocean. I would never do that. And then I ended up 15 years on, then I ended up 15 years on Webb, but it was, you know, when people say, how can you work on something for 15 years? Well, it's a different phase throughout, right? It was completely different every couple of years. It was just a completely different focus and challenge. So,
What was the most difficult of those challenges they're facing from your perspective?
well, there were so many, but the bugaboo that got us in the end was actually the vibration. It worked fine for the measurement of the primary mirror. But when we tried to bounce through all those mirrors and come back through, we couldn't get the vibration down. And what made it complicated was, so your vibration path, you know, comes from the ground up through the chamber, either comes through cables on the floor or comes down through those rods and all that structure suspended from the top of the ceiling and up through the flight hardware. And the problem was, as soon as you passed a certain temperature threshold, everything stiffened up. And you know, it was in the short amount of time period, there's no way we we're going to figure out, okay, where do we go wrong with the assumptions? So at room temperature, everything looked perfectly well. But when you got to that 15 Kelvin, 18 Kelvin, there was far too much vibration. So we had to completely go with a new optical test plan. And so we figured out a way to do it with the vibration that we had and, you know, proved it out. There was two primary things for that measurement. One was to show we knew where the secondary mirror was optically and show that the secondary mirror was working well, but also the whole phasing process that you witnessed as it was on orbit looking at a star. Obviously, we didn't have a star. We had our flat mirrors going back down through. But we had to prove out each step of that process to show that whole process worked. So once it got on orbit, we knew it would work once that secondary mirror was in place. Yes.
How is the Roman Space Telescope coming?
So as I said, we're almost done with the build. We've got the last of the apt optics going in now. Once that gets integrated, then we go through the precision optical alignment, which takes a little time because it's so precise. And then we have to go through all the testing to make sure it can last through a launch. So that happens next year. Then we ship it down to NASA. They integrate it with the instruments, and then they do their launch testing to make sure that there's nothing in that integration that can go wrong. And that includes some of the spacecraft, but not all of it. And then they add the other pieces that are lower risk, like solar panels. So that's why it takes till 2027. The Webb launched from the French Guiana in South America. The Roman is going to launch from Cape Canaveral, so that's a little easier for us. The LISA probably launches from French Guiana, since it's a European Space Agency project. It's a lot smaller. It's three pieces. It's a lot smaller. It probably doesn't need to be in this big a rocket. It's I don't know, from the floor, it's maybe each one of the three pieces is probably like this high, and then this big around. It's not made to view, stars, so that we don't need the huge primary mirror to get faint light. It's actually used to project a laser beam that 1,000,000 miles and hold it very stably so that your sensor, locks onto the laser beam, and you do it in a triangle, and then you wait for a gravity wave to move one of those objects. So it's a much smaller device.
Tony, are you dedicated on these particular projects, or are you like multitasking? You've got other kind of background projects also going on?
Mostly dedicated. These things are big enough and complicated enough. As far as the Webb and the Roman, I mean, on the Webb, my role was just building and testing it, figuring that out, and directing this team of 50 engineers that, included, Germans, French, Canadians, US. So imagine getting all of them on the same page, right? There was other teams who were responsible for like designing the telescope. There are other teams responsible for figuring out how to make the mirrors. There are other teams responsible for figuring out how to make the detectors. So it, huge team. I think there were like 10,000 people that worked on Webb. About 300 from just our company alone.
What a great job.
Yeah. Thank you.
Thank you very much.
Thank you.